Okay, so in this video we're going to take a look at differences between groups using a t-test. I'll talk about how we perform an independent t-test and a pair t-test using RStudio, and most importantly how to interpret it. So I've shown this table before, and it gives you the statistical analysis that's most appropriate to the research design that you are using. So it's dependent on both the independent and dependent variable. If the dependent variable is continuous, that means it's scale, ratio, interval such as VO2 max, heart rate, body weight, number of push-ups, etc., etc. And the independent variable involves only two independent groups or the same sample being tested twice. We have to use what's known as a t-test. And an independent t-test is one in which two independent groups are being compared on the dependent variable, such as males versus females, group 1 versus group 2, stability versus cushioning, right? If you watch my previous video on null hypothesis significance testing, I talked about comparing the mean difference in mile time between stability group or runners wearing stability shoes and runners versus runners wearing a cushioning shoes. For a dependent t-test, however, that can only be used when we're using the same sample or testing the same sample twice. So such as pre versus post, or if I use that running example, I had runners come in who were stability shoe, they ran, and then they ran again with the cushioning shoe. So it's the same sample being tested twice, so we have to use a pair t-test. So in this video we'll go over how to perform each one of these t-tests in RStudio. So I think by now you know how to identify the independent and dependent variables in the research design that ultimately is going to define the null hypothesis. Remember, the whole foundation on which null hypothesis significant testing or inferential statistics is largely based on the probability of observing a result that's either as extreme or more extreme than the one that you found in your observation, given that the null hypothesis is true in the population. And in fact, in that video on NHST, I used a t-test, an independent t-test, as an example of how to interpret that p-value, that probability of error. And we're trying to establish 2 points. Are the groups different? Or can we attribute the differences between groups to the independent variable, to them being a male or female, to them wearing stability or cushioning shoes, whatever that might be? Another overarching concern that we have when we're interpreting the results of a t-test is how meaningful are the differences. Are there any practical or clinical implications of the differences between means? Is 5 degrees enough between FMS scores between males and females, for example? Is 5 seconds between in running time between stability shoe versus cushioning shoe a practical difference? So the meaningfulness or the minimal clinical meaningful difference or clinical meaningful change should be discussed and addressed in the context of the research itself that's being conducted. So that's a different discussion altogether. So some assumptions when running a t-test or an ANOVA, if we're talking about the F distributions, we're just going to concentrate in this video on the t distribution. One, the distribution is normal, right? And it makes that nice bell-shaped curve. The samples that were drawn from the population were randomly done, or participants in our study were randomly assigned to certain groups. The observations are independent of each other. And typically we do this by design. So we use different participants in group A and group B, or I'm looking at section 1 versus section 2, or males versus females. So in those cases, the observations are independent of each other, not correlated. If, however, we're using the same sample and we're testing them twice, which can happen when we're trying to be more productive, and I shouldn't say productive, but more efficient in what we're trying to do in terms of research, and say I'm going to use the same sample of 10 runners and test them twice. We have to use a pair t-test, which takes into account the correlation between groups. In this case, the group is the same, but we're saying the observations are independent of each other in the levels of the independent variable that we're looking at. Another thing is what's called homogeneity of variance. That means that the variances across groups are equal. When you're running a test in either SPSS or in this case we're using RStudio, the test itself will test the assumption of homogeneity of variance and makes adjustments accordingly. In fact, we're going to use what's called the Welch test, which takes into account if unequal variance exists in our data. So don't worry about that too much. You don't have to do anything extra. We're just going to assume, at least in this example, that the variance is actually equal, that the assumption of homogeneity of variance is confirmed. Cool. So in my previous video on null hypothesis significance testing, I talked about the t-distribution, and the t-score gives you the distance that an observed score is away from the null in this case. So we're looking at the mean difference. So in case of a t-distribution, we're looking at the differences between means, difference in mile times between groups, or difference in, we're going to look at VO2 max today, so difference in VO2 max between males and females. And the null effect could be 0, or it could be any number that you considered it to be the same. So for example, some coaches say, well, any differences in mile times less than 5 seconds is considered to be the same. So that's considered to be the null. But in the case of simplicity, we're just going to assume that it's going to be 0. So we want to know how far is that observed mean difference away from the null effect of 0, and we would use a t-score to determine that. And over here on the denominator is a standard error. So that standard error is the uncertainty in our sample when we're drawing our participants and measuring the mean differences in our analysis here. So we measure that t statistic that gives us the distance that the observed mean difference is away from 0 in this case. We look up the critical t and using the degree of freedom, which is calculated off the sample size as shown here, and we compare, and if that t-score is larger or greater than the critical t statistic as based on a dependent variable, then we have a statistical significant result. Another way you can think of it is that if the null hypothesis was true, that there was no differences between groups, the probability of observing that score will be given by that p-value. Is that t far enough from the null effect that we can safely reject or confidently reject that null hypothesis? So like anything, let's take a look at an example, and I'm going to be using RStudio in presenting, well, one, how to run a t-test in RStudio and how to interpret the results. So this is if you're looking at if you're in my research methods class or even my undergrad statistics class, I've used this VO2 max data set quite a bit because it's actually a really good sample, and it illustrates the examples of t-tests and correlations and ANOVA that we use in these series of lectures. So researchers interested in comparing the following 3 variables: heart rate, weight, and VO2 max between males and females. So obviously the independent variable is sex or gender, and the dependent variables are 3 dependent variables, and so we're going to run 3 separate t-tests: heart rate, weight, and VO2 max. What are the null hypotheses, and that is plural, in this example? Correct. That there is no difference in heart rate between males and females, or there is no difference in weight between males and females, there is no difference in VO2 max between males and females. Another way you can think of it is sex has no effect on heart rate, weight, or VO2 max. That's probably a simple way to describe the null hypothesis. We're using independent groups, obviously, because we have one group that's going to be males and another group's going to be females. So let's take a look at it in RStudio. Okay, so now I'm back in RStudio, and the first thing I want to make sure is that all of my RStudio markdown files or scripts and data sets are in my working directory, which is already, which I just by looking at it is already in there. So we're going to be using the VO2 max data set. Make sure you import. I already did it as is shown here, so I'm not going to do it again. I'll go ahead and cancel. So this is the data set that we're going to be using. I'm going to make a blank or use a blank R script. I want to make sure that, again, that the library tidyverse is loaded. Should already be, but you know, just it's always good habit to load your packages into RStudio. I am going to call VO2 data. This it's called the data vector, and place the data set, the VO2 max data set, into this VO2 data. Let's call it data vector. Sorry. We're going to use CSV. That is the type of file that we're entering here. And I already did it, but I'm just show you how I write it here on RStudio. So we're going to look at, it's called VO2 max data.csv. And if you want to test out your code here, just go to the line and just highlight this and hit run. And you scroll down here. If there's no errors given, then you're in good shape. Right here in the console. Okay, cool. So we've got the VO2 data frame or vector. So I'm now going to assign variables to what we're trying to analyze in our t-test. So let's do sex first. That's our independent variable. And we are going to assign VO2, to data. I'm going to put a $sign here so I can choose the variable within the data set that I want. So obviously it's sex. Put that there. We're going to look at heart rate. VO2 data, $sign. Let's do HR. What else we're looking at? Weight, right? Weight. Oops, sorry. Weight. Same thing. VO2 data. And we're going to use weight. And if you get tired here, you can just simply copy and change it. In fact, that's how I do a lot of my coding, is I copy and paste and edit as needed. Hint, hint. VO2, let's say heart rate, weight, and we're going to do VO2 max, right? VO2 max, oh gosh, paste. Let's do VO2 max, VO2 max, and we are going to be using VO2 max. Cool. All right, so now I've assigned the variables into their respected variable names, and we are going to run a t-test, and this doesn't get any simpler than this. We're going to run t.test. The dependent variable in this case, we're going to use heart rate first. We use a tilde sign to indicate we're going to be grouping by sex in this case. Good. And then I'm going to do the same thing for each one of them, for each one of the dependent variables that we want. So the first one's heart rate, the next one is weight. So you don't, gosh, weight. And the next one is VO2 max. Not data, just VO2 max. Good, good. So I've got everything here. Let's go ahead and let's just do the first one. I'm going to include the code from lines 5 to 10. Because first I want to assign those variables, and then I'm going to run the first t-test. So I'm going to hit run, and these are the results for the heart rate. I'm going to run each one of these and then go back into PowerPoint and explain how we interpret the results. So this is a t-test for weight, and then the t-test for VO2 max. Okay, so let's take a look at the RStudio results here. Remember, we're trying to determine whether the mean difference in heart rate, in this case, between males and females, is statistically significant. And so for the first thing we can take a look at here is the actual t value, the t statistic, which is -1 at a degree of freedom. You can see here that the p-value is greater than 0.05. So therefore, the difference in heart rates between males and females is not statistically significant. Therefore, we don't have enough evidence to reject the null hypothesis that the differences in heart rate, or that there are no differences in heart rate between males and females. So again, I hate to belabor the point here. What we're trying to find out here using independent t-test is the probability of observing a result, in this case a mean difference here of 4 beats per minute, given that the null hypothesis is true in the population. In other words, if there was no difference in heart rate between males and females, there is a 29.5% probability of observing a result, in this case a mean difference of 4 beats per minute, in our sample. In other words, what we are observing is what we would expect in the population. 29.5%. Okay, so that is the differences in heart rate between males and females. Let's take a look at weight. So this is the result. That's the t statistic, the degrees of freedom, and the p-value. The mean or average weight in the female group was 70.9 kilograms, and in the males it was 84.3. That is a statistically significant difference in weight here because there is a less than 1% probability of observing this mean difference if the null hypothesis was true in the population. So therefore we conclude, because we can reject the null hypothesis, that there is a statistically significant difference in weight between males and females. Now let's take a look at VO2 max. Same thing here. T is negative 4.7, degree of freedom is 82, its p-value is less than 0.001 in this case. That means the mean difference in VO2 max between males and females, in this case negative 7.5, the likelihood of observing that result or something more extreme or larger than that is less than 1% if in the population there was no difference in VO2 max between males and females. So we conclude that there is a statistical significant difference in VO2 max between males and females. In this case, a difference of, it's negative because we're just simply female. We're subtracting the VO2 max for the female group minus the male group for that of the male group. So in this case, negative 7.5 milliliters per kilogram per minute. So another thing I want to point out here is the 95% confidence interval, which is the plausible range of values that the mean difference might be in the population. So given our sample, the mean difference in VO2 max between males and females could plausibly or likely be between negative 10.6 and negative 4.3 milliliters per kilogram per minute. It's just another way to interpret the results that we get. It gives us an estimation of the potential range of values, in this case mean differences in VO2 max between males and females in the general population. Can we extend what we find in our sample to the population? What you'll find in the literature is the null hypothesis significance test, where we're using the p-value, is more often than not used, but sometimes they'll use confidence intervals, the 95% confidence intervals. Sometimes they'll use both. It's very common among epidemiological research, for example. But anyway, that's how you would interpret that 95% confidence interval. Okay, so now let's take a look at a dependent t-test. Very simple example here. We're going to use volleyball. Say the volleyball coach is interested in serving accuracy for the varsity squad at the beginning of the season, and then at the end of the season, the coach tests the players pre and post on serving accuracy. Null hypothesis, obviously, that there is no difference in serving accuracy between pre and post time points. And the alternative is that there is a difference. So what we're trying to find here is a change in serving accuracy over time, right? It's the same sample being tested twice, pre and post season. If we were to do the math, this is how we would calculate that t distribution or the t-score. Don't worry about it, I'm not going to have you calculate this by hand, but just know that it's dependent on the effect. So the difference between the post serving accuracy and the pre-serving accuracy, as well as the uncertainty. So this is the standard error that's used when we're looking at repeated measures. In this case, the same sample being tested twice. Let me show you how it looks. In our studio, these are the serving accuracy in the preseason versus the postseason. I think you could tell here that just by looking at it that the postseason accuracy scores actually improve. What we want to know is that improvement, is that change statistically significant? So we're going to go into our studio and run a t-test. Okay, so let's do this in our studio. I'm going to run a pair of t-tests on that data set I just showed you. First thing I need to do is make sure that I import and make that data set active in our studio. Let's call it VB data. And I'm going to read in that data set, which I believe the original file is an SPSS. Let me double check here. I believe it is. It would be table 5.5, and if you've taken my undergrad statistics course, this is the same data set I've used to describe the pair t-test. Yep. So that is table 5_5.sav, which is a traditional format for SPSS. I'm going to go ahead and run it. Cool. So now I have all the data set into the data vector called VB data, and we want to double check that to make sure that you have it. Just go down here to the console, type in view VB data, hit return, and it shows up there. Cool, so everything's in there. Now let's run a PR t-test. Same thing, I'm going to assign the variables from the data set here. I'm just going to call it pre, and we are going to assign the pre, obviously the pre, nope, not $, there we go, pre-season accuracy score, serving accuracy is what we're measuring. And then post would be VB data $. And if you're taking my research methods course, I'll have both of these R scripts as well as the data set up on Canvas, so you can download and try this on your own. Okay, so I got pre and post, and it's always good to comment. Let's say pre and post serving accuracy. Gosh. Let's see, it's all pre and post season serving accuracy. Okay, so we're going to run a t-test. T-test, we want pre versus post, and we're going to make sure that this is a paired t-test. Remember, it's the same sample being tested twice, pre and post. So we'll call this paired equals true. Okay, I'm going to go ahead and select these 3 lines of code, run that, and voila, that's our t-test. So let's take a look at the results here. Okay, so it's very similar to the independent t-test. The only difference here is now we're looking at the difference or change in serving accuracy from pre to post. This is the t statistic and the p-value here, as well as the differences in pre and post means. So the change in accuracy is 3.4 roughly, and it is statistically significant because there's less than 1% probability of observing this difference if the null hypothesis was true in the population. So therefore we have enough evidence to reject the null hypothesis and conclude that the difference in serving accuracy is statistically significant, and we can attribute that to training, whatnot. In fact, if I were to redo the study, I would actually have 2 groups that will be tested pre and post. One that does a particular type of training versus a control group, and that would determine the effects of both time as well as training on serving accuracy. So anyway, that's how you interpret that result.